Welcome to Lesson 11 and Part 2 of the course. Over the first 10 lessons in Part 1 of the course, we learnt all about Arm's weakly ordered memory model, which permits memory accesses satisfying certain conditions to be freely reordered with respect to one another. And we saw that we need to use explicit data memory barrier instructions, DMBs, in software so as to manually enforce ordering between memory accesses that would otherwise be reorderable, when such reordering might have a functional impact on the result of our program. Now, in my experience teaching about barriers, there's a risk here at this point that barriers are just seen as being these fuzzy, esoteric, or even abstract tools, and you're likely asking yourself, what are these barriers actually doing in hardware, and how are they actually enforcing ordering? And so I find this to be a good opportunity for us to take a step back and spend some time exploring how barriers are implemented in hardware. In order to do this, we first need to understand how cache-coherent interconnects work, as it's the transactions flowing through the interconnect fabric that are actually being ordered by our barriers. So that's going to be the next 4 lessons. We'll then build on that understanding by exploring how barriers work when they're being broadcast onto the interconnect for it to handle on behalf of the CPU, followed finally by comparing and contrasting that to how barriers work when they're instead being handled internally to the CPU based on completion responses from the interconnect. Now, granted, it's actually fairly rare nowadays to see a modern system in which barriers are being broadcast onto the interconnect for it to handle on behalf of the CPU. Most modern systems nowadays instead handle barriers internally to the CPU based on completion responses. That said, I still find it's a really useful learning exercise to explore how both techniques work. Firstly, because the approach of broadcasting barriers onto the interconnect is really very visual, so it lends itself really well to being drawn in diagram form, and that makes it great for training presentations like this. But also because exploring 2 different techniques reinforces the idea that if you want your software to be truly portable across systems, then it's important to write your code to be architecturally compliant rather than relying on the behavior of a specific implementation. On that note of relying on the behavior of a specific implementation, so a big warning/disclaimer here, it is very much beyond the scope of the ARM architecture exactly how things like cache coherency and barriers are actually implemented in hardware, and there are many ways of doing it. So the microarchitectural implementation-specific details that we'll be exploring over the next few lessons are just some examples of how it can be done. Furthermore, for the purposes of these lessons, we will be deliberately conflating certain aspects of the AMBA-AXI-ACE and AMBA-CHI bus architectures. We'll also be abstracting away and simplifying some of the finer details for educational purposes. So while what we'll be discussing here really does closely align with how it really works on ARM-based systems using AMBA-based interconnects, do keep in mind we're not trying to accurately reproduce the AMBA-AXI-ACE and AMBA-CHI specs here. Also remember that not all ARM-based systems are using AMBA-based interconnects in the first place, so other bus architectures do exist and they're just as valid for use as AMBA. So with all that said, let's begin with a quick refresher of some of the concepts that we first briefly touched on back in Lesson 2, but taking the time to explore them in a little bit more detail. So conceptually speaking, a system can be thought of as being a collection of nodes, where each node can be broadly categorized as either being a request node, a home node, or a subordinate node. A request node is anything capable of issuing transactions to the interconnect. So this could be a CPU or a cluster of CPUs, could be a GPU, or it could be some other DMA-capable peripheral device. A subordinate node is typically an interface to memory, so for example, a DDR controller, or it's an interface to one or more I/O peripheral devices that are not themselves capable of issuing transactions to the interconnect. So these could be things like a non-DMA capable UART, some GPIO pins, maybe a flash controller. Now, when a request node wants to access a particular subordinate node, whether that be in DDR space or in I/O space, that request node cannot simply access the target node directly. Instead, the request node must first send a, request to the corresponding home node. So these home nodes basically sit in between the request nodes and the subordinate nodes, with each home node then being assigned to manage a specific range of addresses in the system. Now, this here actually represents the first example of us deliberately conflating AMBA-AXE and AMBA-CHI for educational purposes, because technically speaking, home nodes were first introduced as architected components in AMBA-CHI, and they were not a part of the older AMBA-AXE. Even so, conceptually speaking, you can still think of ACE-based interconnects as having some sort of logic block that is functionally equivalent to a home node. It's just that that would be considered to be a micro-architectural implementation detail of an ACE-based interconnect, rather than it actually being an explicit part of the architecture itself. In AMBA-CHI, this is no longer abstracted away from us, and home nodes are an explicit part of the architecture. So just keep that in mind. Now, what these home nodes actually do is serve as the single point of serialization for all transactions targeting their assigned address range, meaning they are responsible for establishing order between those transactions. To understand what I mean by that, it's worth us digging a little bit deeper into the actual underlying structure of the interconnect. You see, this diagram as you see it here is really more of a high-level or abstract view of the interconnect. And in reality, if we were to dig a little bit deeper, then we'd see that the interconnect often takes on a sort of mesh-like structure, as you see here. You may remember me promising to revisit this diagram in a future lesson, so here we are. Now, despite looking quite different, these two diagrams are actually describing the exact same system. Both diagrams have our set of example request nodes, so a CPU, a GPU, and some other DMA-capable peripheral device. Both diagrams have our set of two example subordinate nodes, a DDR controller and an I/O bus. And both diagrams have our three home nodes as well. The main difference here, of course, is that the diagram on the right shows that this particular interconnect is actually built up of several so-called cross-point nodes, arranged in a 2x2 mesh configuration. These cross-point nodes serve a similar purpose to a switch or router in a traditional computer network, except that while a traditional switch or router will be passing along IPv4 or IPv6 packets from source to destination, these cross-point nodes are passing along memory transaction packets from source to destination. So, I mentioned earlier that the home node serves as the single point of serialization for all locations in its assigned address range, meaning it is responsible for establishing order between those accesses. I like to think of this as being a bit like a funnel, where there may be various request nodes all around the system, all trying to access the same location at approximately the same time. So this funnel is quite wide at the top, collecting up all of these different accesses, but then the funnel gets narrower and narrower towards the bottom, until we can only fit through a single access at a time, meaning the accesses need to pass through this choke point, single file. And indeed, it is the home node's job to basically arbitrate between all of the different accesses that are arriving there and to choose which access should be processed first. In other words, it serializes those accesses, hence point of serialization. And this has important implications for us. So, since the transactions targeting a specific home node are being issued by different request nodes, they may take different paths through the interconnect fabric to get there, and those paths may therefore be of different lengths, meaning those transactions may arrive at the home node in a different order to the order in which they were first issued to the interconnect. And so it's the order of arrival and processing at the home node that actually establishes order of observation between different request nodes. For example, if we just focus in on our mesh network diagram on the right here, it may be that our CPU issues access A to some location being managed by this home node down here. And so that memory transaction packet begins propagating through the interconnect fabric towards that home node. Some short time later, our GPU may issue access B to the same location. And so that packet also begins propagating towards the same home node. And since access B does not need to travel as far as access A to reach that home node, it is entirely possible for access B to arrive there before access A, and to then be serialized first, despite having been issued to the interconnect later. Now, quickly revisiting our two diagrams side by side, you may have noticed the fact that the I/O subordinate node has been assigned to exactly one home node, while the DDR controller appears to have been assigned to two home nodes. And this is perhaps a little bit easier to see when looking at the conceptual diagram on the left, as we have these two red lines joining the home nodes directly to the DDR controller. So what's going on here? We'll recall that one of the driving design goals of modern cache-coherent interconnects is to be scalable. That is to say, to minimize the potential degradations in system performance associated with having more and more request nodes and larger pools of DDR memory. We want systems that can scale up to having hundreds of CPU cores and hundreds of DMA-capable peripheral devices, while also having hundreds of gigabytes to several terabytes or even petabytes of DDR memory, all without compromising overall system performance. So what we do is carve up our DDR space into several so-called slices, and we then assign each of those slices to a specific home node for it to manage. In doing so, we're able to load balance DDR memory traffic across a number of different independent home nodes, rather than having all DDR memory traffic always be converging on a single point. This also enables us to distribute our system-level cache through the interconnect fabric as well. So each home node will have its own slice of the overall system-level cache, specifically used for caching the locations managed by that home node, and which is located physically nearby to that home node on chip. And that's what you're seeing in this diagram here. So we've carved up our DDR space into two slices, and we've then assigned each of those slices to its own independent home node. Okay, so that was a quick refresher of some of the concepts that we first touched on back in Lesson 2, and what I want to do now throughout the remainder of this lesson, and also throughout the next lesson, is start walking through a few different scenarios with you in order to give you a better idea of how these nodes are actually communicating with one another. So what the memory transaction packets actually look like, and how the nodes then respond to those packets. Firstly though, let's hide the conceptual diagram on the left, as we'll be focusing on the mesh network diagram on the right when walking through these scenarios. And we'll just nudge that across a bit as well to give us some more room on the slide. And finally, let's just quickly label our various nodes here. Firstly, for our request nodes, we'll say that we have two CPUs, P0 and P1, along with some other DMA-capable peripheral device, which we'll label E2. And remember, we're using these particular labels in alignment with how these kinds of scenarios are typically presented in the ARM architecture reference manual. And then for our home nodes, we'll label the two home nodes managing DDR space as H3 and H4 respectively, and we'll label the home node managing I/O space as H5. And let's begin by considering this as our first scenario. So P0 wants to read some data at a particular address in DDR memory, where that address has been mapped as normal cacheable in the page tables. So what's going to happen here? How does this actually work? Well, the first thing P0 is going to do is look up in its own private caches to see whether it already has a copy of that data. If it does, great. That data is simply loaded into the CPU's internal registers and we're done. If, however, P0 misses in its own private caches, then it will issue a transaction to the interconnect requesting a copy of the corresponding cache line. And specifically, P0 will issue what we call a read shared transaction, which basically tells the interconnect to give me a copy of this cache line, and it's okay if other agents in the system retain a copy in their own private caches too. That last bit's important, and we'll come back to why in the next lesson. So this read shared transaction begins propagating through the interconnect fabric towards whichever home node is responsible for managing that particular cache line. And let's say that's home node H3 for the purposes of this example. Upon receiving this transaction, the first thing home node H3 does is looks up in its own slice of the system level cache to see whether it already has a copy of the requested cache line. If it does, great. It can simply return a copy of the cache line back to P0. On the other hand, if home node H3 does not already have a copy of the requested cache line, then we're going to need to go and find a copy of that cache line. So how do we do that? Well, we could simply go and ask the DDR controller for a copy, but of course, there's a possibility here that some other agent in the system, like say P1, has a copy of the requested cache line in its own private caches, and, crucially, P1's copy of the cache line may be in a so-called dirty state, meaning it has been written to at least once since being loaded from main memory, and that write has not yet been synced back to main memory. In other words, if we were to simply load the requested data from DDR here, then we'd actually be loading stale, out-of-date data. And that's not good. So we cannot just go straight to DDR if we miss in the system level cache. Instead, what the home node does is sends what we call a snoop request to the other agents in the same shareability domain as P0, asking them to provide a copy of the requested cache line if they have it. In this particular case, that means H3 sends a snoop shared to P1. Now you'll remember P0 sent a read shared, which meant give me a copy of this cache line and it's okay for other agents to retain a copy. And this snoop shared then correspondingly says to P1, give me a copy of this cache line if you have it, and it's okay for you to keep your copy. So P1 will respond to this snoop request by either providing a copy of the requested cache line or by informing H3 that it does not have a copy of the requested cache line. If it did have a copy, great, we can send a copy back to P0. Or if P1 informed us that it did not have a copy, well, now we can go and ask the DDR controller. And you'll notice that the packet that's actually sent from the home node is a read no snoop, which indicates that this transaction should not generate any further snoop requests into any other agents. In response to this request, the DDR controller returns the requested cache line back to H3, and finally, H3 can return a copy back to P0. So that's the basic flow when P0 wants to read some data from DDR where that page has been mapped as normal cacheable in the page tables. However, there are some further considerations to be aware of here. And furthermore, there are some small but very important differences between this flow, where we're reading from cacheable data, versus what happens when we're instead writing to cacheable data. And that will be the topic of our next lesson. I'll see you there. Thank you.